I just guessed that I had a hunch and I tried a lot of stuff and I found an example.
Is your theorem for distinguishing advantage like 1, or for like any 1/2 plus epsilon distinguishing you turn into some gate and dependence over epsilon, or some other circuit that's dependent over epsilon?
Can you repeat it?
So you said that if you have a distinguisher between plus and minus states, then you get some other circuit. If my distinguisher only has like 1/2 plus epsilon distinguishing advantage, how does that translate into the resulting circuit?
So I don't remember exactly, but yes, we have a theorem about it.
I see. So you basically amplify this to 1 and then you can turn it.
No, you cannot. Actually, there are cases where you cannot amplify. Okay, so the last talk is by Nilin, who speak about Chernoff, spectral Chernoff bands for local Hamiltonians.
All right. Yeah, so I'm Nilin. I'm a postdoc here at the Science Institute and in the math department in Berkeley. And yeah, so I'll talk about local Hamiltonians. So it's a many-body quantum system with n qubits. So you have this exponentially large state space and m interactions. M could be of larger order than n. And so you can draw the interactions as the hyperedges on this graph where the vertices are the qubits. And so each interaction acts on these, just a few of the qubits. We will demand that the interactions only act on a constant number. So that's a local Hamiltonian. The local Hamiltonian is the sum of these individual interactions. And this is motivated in many different ways. You can see it as a quantum constraint satisfaction problem, or and it can also represent fermionic systems. So now I want to think of an approximation setting. So for approximation theory, you might want to rescale like this. So you divide by the number of interactions. So with this rescaling, the spectrum is, you guarantee that it's in the unit interval. But even so, it's still potentially hard to approximate eigenvalues up to a small constant error. So by the classical PCP theorem, it's NP hard to approximate it up to some small constant error. And it's conjectured that it's for local Hamiltonians even harder, so conjectured to be QMA complete. Now, okay, so that doesn't make the problem easy, but I want to introduce another level of approximation. So instead of trying to resolve the individual eigenvalues, let me try to get an idea of what the spectrum looks like, sort of what the bulk of it looks like. So so we think of the we take the spectral measure, which is just you place a mass at each eigenvalue, and then you normalize it to be a probability measure, right? So given the local Hamiltonian, can we get an idea of what this looks like? Okay, so let me try to make an algorithm for this. And so how might we try to approximate such a distribution? Well, we try to approximate the moments, right? And to get a small constant error in the Earth mover distance, we only need a small constant number of moments. Okay. And now, thankfully, we can compute the pth moment for p constant, because this is the sum of the pth powers of the eigenvalue, so it's a trace of the Hamiltonian to the pth power. Now, because of locality, we just we can expand the sum that defines this H. So we get this p-fold sum. Now, each of these small h's here is local. So when p is constant, this is also local. So this we can compute. And so we just end up with a time that grows as the n to the p terms here. So, we can get an idea of what the spectrum looks like in polynomial time. Okay, so this seems nice. So unfortunately, it won't give us anything too useful. And so what you'll find is that it just gives you, the information it gives you is sort of universal to, and just follows from the locality. And to see this, let's try to do it by hand. So there's not so I drew like a complete graph here to say that we don't have to have spatial locality or anything like that. So we might have a large degree, for example. So if we try to use the method from before to find the variance of the spectral distribution, note that the Hamiltonian is deterministic, so there's no randomness here. Variance just means just to quantify the spread. So we'll see that many of these terms will end up being trivial. So whenever the two interactions don't overlap, you'll get 0. And so most of these terms will end up being trivial, and more precisely, we can sum over the first I here, and then the second one. For each choice of I, there'll only be sort of G choices of the other one that overlaps, where G is the degree. Okay, so in the end, we get that the second moment goes to 0. And yeah, so this is sort of a Gaussian concentration, it looks like, with deviations of order 1 over square root n. Don't use any randomness here. So this sort of gives us the concentration in the horizontal direction, but question is, do we actually get something that looks like an actual Gaussian concentration? So it turns out that you do. Okay, so the spectral measure will concentrate exponentially. A similar result was shown recently also by De Palma et al. But the proof here is very simple. So we can take the Hamiltonian and split it into, make a coloring of the hypergraph. So we split it into matchings, meaning that we split it into subgraphs where in each subgraph, none of the interactions overlap. And then for each color, we apply the Chernoff bound. So for each color, this becomes a classical problem because the spectral distribution will just be a convolution. And then we'll use the fact that so to get the speed of concentration will depend on the number of edges within that color, within that matching. And so we lose something if we have many colors. On the other hand, we gain something if we have many edges. And these two effects cancel out. So in the end, we get a concentration that's exponential in n. Now we might ask, could we have gotten even better? So exponential in m in the edges. But that's not the case, because if we just look at a single eigenvalue, that'll its weight will be exponential just in n. Exponentially decreasing in n. So this is the actual form that we want. And then we can combine these using eigenvalue inequalities. Okay. So yeah, so that gives a simple proof to show some universal properties that of the spectrum of a Hamiltonian that follows just from locality, no randomness. All right, thanks.
Thank you. Any questions?
Could the concentration be shown against other distributions as well? Like this is sort of a uniform distribution, right? Like
What do you mean against?
I mean, this theorem could be seen as concentration of the energy for uniform distribution on the qubits. Could you generalize it to other product distributions?
So I'm not sure I understand this question. So do you mean maybe you mean that the interaction strengths are all sort of uniform here?
I know. So it's the same Hamiltonian.
Yeah.
But you're looking at the probability that a uniform distribution, the uniform state would fall under a certain energy window.
Oh, yeah, yeah.
But you could ask for other distributions as well, not just uniform. You could ask the same question for any root incident and ask what is the probability that falls under a window.
Oh, yeah, yeah. So for a different distribution of that, well,
Yeah.
yeah. So it doesn't, yeah, it doesn't follow directly because there'll be some issues applying that values inequalities. But yeah, so I'm not sure if you can do that. Yeah.
Great. Well, let's thank all the speakers for this session. There's a short break now for the next session.